To solve logic and navigation problems, artificial intelligence models the physical world as a mathematical environment called a state space. The AI defines a starting configuration, an initial state, and calculates a precise sequence of actions to reach a defined goal. Every search environment requires specific parameters to function. The model needs an agent to act, an initial state to start from, a set of actionable choices, a transition model dictating the results of those choices, a test to verify if the goal is reached, and a path cost to measure efficiency. The AI tracks its progress using data structures called nodes. When the algorithm expands a node, it logs the current state, the parent node that generated it, the action taken, and the total path cost. These nodes are managed in a pending queue known as the frontier, while an explored set logs past possessions to prevent infinite loops. Correctly defining these parameters is mandatory. Without a structured state space, an AI has no mechanism to distinguish between a successful solution and a failure. Uninformed search algorithms navigate without problem-specific knowledge. On a maze grid like this, depth-first search relies on a last-in, first-out stack structure. It plunges down a single path until it hits a dead end, forcing it to backtrack. This blind approach can find a solution, but it often yields bloated, suboptimal routes. In the same maze, breadth-first search replaces the stack with a first-in, first-out queue. Instead of diving deep, it explores the environment outward layer by layer. In unweighted environments, this structural change ensures the algorithm will find the absolute shortest path. This layer-by-layer expansion is required for mapping the shortest sequence of shared movies between two Hollywood actors. To find a specific goal node, like Kevin Bacon, the AI explores all cost 1 connections first, then all cost 2 connections, ensuring the tightest possible linkage. The choice of data structure determines the outcome. Deciding between a stack and a queue dictates whether the AI secures the mathematically shortest path or wastes resources on massive inefficiencies. To optimize navigation, engineers use informed search. This logic injects problem-specific heuristics into the algorithm, like estimating the Manhattan distance to a target. This allows the AI to prioritize nodes that move geographically closer to the goal and ignore paths that move further away. This approach culminates in the A-star search algorithm. A-star evaluates a node by adding the exact accrued cost of the path so far to the estimated remaining cost to the goal. As long as the heuristic never overestimates the true remaining distance, a property called admissibility, A-star is mathematically guaranteed to find the perfect route with minimal wasted computing power. Standard navigation environments are static, but adversarial search environments, like a game of tic-tac-toe, introduce an active opponent whose objective is to force the AI to fail. To solve zero-sum games, the Minimax algorithm standardizes the board into mathematical win conditions, assigning a +1 for an AI victory, a -1 for an opponent victory, and a 0 for a draw. The AI simulates every possible future board state. It calculates the optimal move by assuming the human opponent will play perfectly to minimize the score, while the AI selects the action that will strictly maximize its own outcome. Minimax removes the need for guessing. By pre-calculating every countermove, the AI forces a win or a draw, rendering these deterministic games mathematically solved. Selecting the right search algorithm determines whether these logic puzzles are solved efficiently or exceed the limits of a system's memory and time. Whether navigating through social graphs, solving physical grids, or mapping decision trees, state space search provides the mechanism for an agent to move rationally from an initial state to a goal.